Okay, for section 7.2 we're going to look specifically at linear functions, graphs of lines, etc., and equations for lines. So bottom line is the general formula here. All equations of the form ax plus by equals c are straight lines when graphed as long as a and b are not both 0. And these are called linear equations in two variables. So again, a, b, and c can be any number except for a and b cannot both be 0. Because if that were the case, then we'd have 0 equals some number, which would be a false sentence. So a couple things that we need to know about graphing a line that's in this form. We generally call this standard form. Okay. So if we have a line that's in standard form, okay, the best way to draw a graph of that line is to find the intercepts. Okay. So in general, locating the intercepts, and this is going to be true for any kind of function. It's true for linear functions, but it's true for every kind of function. If we want to locate the x-intercept, and in some cases, some functions have more than one x-intercept. In the case of a line, there's only one. But to find the x-intercept, what we're going to do is we're going to set y equal to 0 and then solve the equation for x. Okay, when we set y equal to 0, that means we're going to plug 0 in for y and then solve the equation for x. And if we want to find the y-intercept, we're going to do the opposite. We're going to put 0 in for x, and then we're going to solve that equation for y, and that's going to give us the y-intercept. And again, the reason why that's a fact is because if we're looking for an x-intercept and we are on the x-axis, that coordinate would be something like a0. Okay. The y-coordinate would always be 0, so if we plug 0 in for y and solve for x, we're going to get the x-intercept. Opposite would be true, of course, for the y-intercept. So if we look at the equation that we're given that we need to graph here, it says to graph 3x plus 2y equals 6. So if we're going to do that, we're going to make an xy chart, and we're going to put in 0 for x and solve for y, and then we're going to put 0 in for y and solve for x. So the first part, it would look as follows. Okay, we want to find the x-intercept. We're going to let y equal 0, so we're going to plug a 0 in for y. That'll leave us with 3x on this side, 6 on this side. If we divide by 3, we'd get 2. So the x equals 2 is the x-intercept. And similarly, if we do the y-intercept, if we put 0 in for x, we're going to get this to be gone. We're going to be left with 2y equals 6. And then if we divide by 2, we're going to get y equals 3. So these would be the two intercepts. And if we wanted to graph those two on our coordinate plane, again, we have x equals 2, so that translates to the point 2, 0. Here's our x-intercept. And our y-intercept was 3. That means we're going to cross the y-axis at 3. So our y-intercept would be 0, 3. And if we have those 2 points, then we can sketch our line. And again, any graph that we draw should always have arrows on it, provided that it continues in both directions. In this case, it does. So that would be our equation graphed using intercepts to graph that linear equation. Now, one other common fact that we deal with lines is that each line that we deal with has a slope, except for a vertical line. Okay, all lines are going to have a slope. Okay? And ultimately, to calculate that slope, we're going to use our slope formula, which is y2 over y1 minus x2 over x1. Okay, and those numbers that we're going to plug in here, there's 4 numbers to plug in, are going to come from our points that we're given. And the notation here just means the first x and the first y, second x, second y. So we're going to subtract the y coordinates on the top, subtract the y coordinates on the bottom, and then divide. We'll leave it as a fraction, of course. Even if it's improper, we'll leave it. Okay, and ultimately this is going to give us our change in y over change in x, which we call generally the rise over the run. Okay. Now, when we go from this point to this point, again, the rise is the change in the y coordinates, the run is the change in the x coordinates. Okay, so what we have to be very careful with is that we actually put the y coordinates on top, subtracted the y coordinates on the bottom as well, or x coordinates on the bottom, I should say. So let's go ahead and using the definition of a slope, it says find the slope of a line that passes through these two. So if we write down and we generally use m to represent the slope. If we do y2 minus y1, x2 minus x1, okay, our y2 in this case would be the 4, because that's the second y, minus, and then y1 is the first y, which would be -1. And notice when I put that in there, I put it in parentheses. Even if this was positive, I'd still use parentheses here to be careful. And again, make sure it's subtracting. And then my x2 would be -2, and then minus, and then -3 would be my x1. And then from there, it's just a math problem. Okay, we have calculators, so hopefully we can do this without it, but if we have to, we can calculate it with that. But that said, it'd be 4 minus minus, so it becomes a plus, so we'd have 5 on the top. and then this would also become minus minus becomes a plus, so it would be negative 2 plus 3, which would be 1, and so in this case our slope would be 5. So if we were to draw those 2 points on our coordinate plane, which I will do now, okay, negative 3, negative 1, okay, and then negative 2, 4, would be right there, and if we were to draw the line that connects those two, okay, it would have a slope of 5, because notice that it would rise 5 and run 1. Okay, so illustrating that value of that slope in rise over run terms. Okay, because again, 5 as a whole number, as a fraction, 5 is 5, but as a fraction, it would be 5 over 1. Okay. All right. Now, one of the things that we're also going to deal with is equations for lines besides the standard form equation. This is what we call slope-intercept form. And ultimately, when we have an equation that's given to us in this form, we can see both the slope and the y-intercept right straight from the equation. So in this case, 2 is the slope, negative 4 is the y-intercept. In this case, a half is the slope, and 2 is the y-intercept. Okay, one thing that we want to make sure we don't ever do is that, like in the case of the one above here, okay, we don't ever want to say slope is 2x. Okay, so the slope is not 2x, the slope is 2 instead. The slope is a number, it's not a variable in this case. It's the number that's in front of x, it's the m, it's not mx. Okay, so make sure you're careful with that and don't say that the slope is 2x. Okay. Alright, so ultimately one of the things that we want to be able to do too is if the line is given to us in this form, y equals mx plus b, we'd like to be able to draw the equation, draw the graph of it using that information. So in this case, we're going to use the y equals mx plus b, and these are the set of steps that we're going to use. First step is to plot the point containing the y-intercept. This is the point 0b. So we're going to plot the y-intercept. So as an example, if we were to do y equals 2x plus 4, okay, on my graph, if I did step 1, I would go ahead and find 4 on the y-axis and I would plot it. So there's 1 point. And then part 2 says obtain a second point using the slope m. Right, m as a fraction, use rise over run starting at the point containing the y-intercept, and then plot this point. So in our case, our m is 2, which is 2 over 1. So from this point that I just graphed, I'm going to rise 2, and I'm going to run 1. So rise 2, run 1, and I'll make another point. So rise 2, run 1, and once I have that done, then I have my graph. Okay. Similarly, if I had to do y equals, let's say, negative 1/2 x plus 1, and I would plot the y-intercept. There it is at 1. And this time when I have a negative here, what I want to think about is making sure that I consider the negative to be on the positive. So that means I'm going to rise negative 1, which means I'm going to go down this time, and I'm going to run 2. And when we do that, as long as we always put the fraction, if it's negative up, we always put the negative on the top of the fraction, then we can always think of the rise part as either up or down, and then the run is always to the right. Okay. So if we go down 1 and then over 2, and we draw our graph as such, and that would be the graph of negative 1/2 x plus 1. Y-intercept of 1, rise negative 1, run 2, and that gets us our second point. All right. So, that said, the other equation that I have here to take a look at is 2x plus 5 equals 0 by using the slope and the y-intercept. So in this particular case, we can't see the slope and the y-intercept because it's not in the right form. So what we need to do is change it to the correct form. So let's look at the algebra that it's going to take to do that. Ultimately, we want to write this as y equals mx plus b, so therefore we're going to solve for y. So to solve for y, we're going to subtract 2x from both sides. Get that 2x over to the other side. Okay. And then we're going to divide by 5. So when we get done dividing by 5, we get our equation, which is y equals negative 2/5 x. Okay, and at this point, now we can see that the y-intercept is, there'd be a plus 0 here, if you will. So the y-intercept is going to be the origin. Okay, and then we would rise negative 2, and we'd run 5. So in slope-intercept form, okay, we change it to that. Okay, once again, we'd plot 0, 0 at the origin, and then we'd rise negative 2, and we'd run 5. And that would give us the second point, and therefore we could draw those, draw a line through those two with arrows, and we're good to go. Now, a couple of special kind of lines that we're going to also deal with are horizontal and vertical lines. Okay, if I have a graph that's y equals b, okay, just some constant, there's no x involved, Okay, notice there's no x. And if there's no x, then it is a horizontal line and it has a y-intercept of b. Okay. If it's a vertical line, it's x equals something. Okay, that means there's no y. Okay. If it's a vertical line, there is no y here. And we would have an x-intercept of a, and we would draw the line right straight through those points. Okay. So, looking at an example here, we have to graph y equals 4 in the rectangular coordinate system. Okay. All ordered pairs have y-coordinates that are -4. So no matter what we pick for x, it's totally our choice. We're going to have a y-coordinate of -4. And if we plot all those points, we're going to see a horizontal line. Okay. So once we do that, if we plot those points, we're going to get the horizontal line at y equals -4. Then again, do you really have to plot all 3 points? Not necessarily, because if you recognize that it's a horizontal line, you can just find -4 on the y-axis, okay, and draw a horizontal line through it. Okay. Okay. Similarly, if we have x equals 2, this would be an example of a vertical line. Okay. Every x-coordinate is going to be 2 no matter what y-coordinate it is, and if we plot all these points, they will be in a vertical line to each other. And so on the next page, we've done that. X equals 2, we can just find 2 on the x-axis and draw a vertical line through it, and that would be the line x equals 2. A couple other notes here about vertical lines. No vertical line represents a linear function. Okay, remember, this is not a function because it does not pass the vertical line test. Okay, all other lines are graphs of functions, so any other line that we draw besides a vertical one would qualify as a function because it would pass the vertical line test. Okay. A couple other notes about horizontal and vertical lines. Okay, just to illustrate, we have y equals b. It's a horizontal line, y-intercept. We've talked about that. Same thing with the vertical line being a with the x-intercept. Okay. And then what we're also going to talk about here is slope. Okay. Another idea regarding slope. Slope is defined as the change in y over the corresponding change in x. Okay. It's also interpreted as the rate of change because in problems that involve real life situations, okay, slopes are always going to be rates of change. So let's look at an example. This would be the graph of shows the cost of entitlement programs for 2007 with projections through 2016. The slope of the line represents representing Social Security. Okay, so describe what this slope represents. Okay, if we look at if we were to calculate the slope of the Social Security line, let's say, okay, and we subtracted the tops here. Okay, this is the cost in billions of dollars. Okay, and then the years are going to be our x-coordinates. And think about if we had y over x in this case, we'd have billions of dollars on top, and we'd have years on the bottom. And that slope ultimately is a rate of change. And think about the units would be billions of dollars. And when we divide, we say per. Okay, and in the bottom is years. So ultimately, the slope, when we calculate it, would give us a measure of billions of dollars per year. Okay, which again is a rate of change. Right. So in the case of the Social Security one, they actually calculated that on this slide. They wrote down the 2 points. Okay. And then on the next one, we're going to calculate that rate of change. Okay. It turns out to be 388 over 9, which ends up being 43.1. Okay. And again, it's 43.1 billions of dollars per year. So 43.1 billions of dollars per year. Okay. All right. And then the last part here, linear functions are useful for modeling data that fall on or near a line. Okay. If you watch the part 2 video, I'm going to illustrate how we model data, okay, with linear functions.